Okay, so next up we have Shreya. And so she is going to be speaking about using machine learning to predict charge depletion patterns in electric vehicles. So Shreya, I think what I will do is share the screen and I'll do the slideshow. Let me know when you want me to turn, switch slides, okay?
Sure, sounds good.
So whenever you'd like to get started.
Okay, great. Good morning, everyone. My name is Shreya, and I am a rising senior at Design Tech High School, and I will be presenting a little bit about my research paper titled Using Machine Learning to Predict Charge Depletion Patterns in Electric Vehicles. And you can switch sides. Thank you. So as you all might have noticed, electric vehicles are gaining in popularity for numerous reasons, attracting support from politicians, green energy advocates, and businesses alike. In fact, President Biden recently allotted a sizable amount of funding for electric vehicles and their industry, and has made statements in support of the United States going fully electric relatively soon. Reasons for this change range from impending effects of irreversible climate change to business opportunities and in general advancing technology. You can switch sides. However, there are still a lot of reservations about electric vehicles. As you can see on your slides, more than half of American adults oppose the phase out of gas cars. So why might this be? A big concern is reliability. Picture this: a family takes their electric car out to a camping trip. It's hot, the AC is running, and they're driving over hills while using a multitude of other car features. These things and many other things affect the charge of their car. The battery percentage starts to show that they have very little power left while they struggle to find nearby chargers. A very likely possibility in this situation is that they could become stranded and without cell phone signal could be in serious danger. However extreme the situation may seem, this scenario is a cause of concern for many. But how could they have avoided this situation? Like I mentioned, the charge left in the battery is dependent on multiple things, and it can change unexpectedly at any time. How do we know that their car will predict the right amount of charge left? Compared to electric cars, gas cars are much simpler in planning for fuel. Besides, a big problem is that it isn't well known how electric vehicle manufacturers even predict the state of charge and how accurate these predictions are. Next slide. To address these concerns, I decided to run some experiments of my own in the hopes of proving that the EV state of charge prediction can be done easily and accurately. This experimentation process can be broken down into three major parts: the consolidation of data, where I took the appropriate data and used delta and stagger values to determine the best intervals to measurement. Second, feeding the data to algorithms and recording this for all the different data sets while looking at the errors in context. Lastly, I compared the lowest error rates within different data sets and concluded whether the experiments were accurate enough or not. The end goal was to see if I could predict the state of charge given data on the other features of an electric vehicle, because state of charge, like I said, is one of the most dynamic data points of the car, and inaccuracy could lead to customer dissatisfaction and on the extreme end, dangerous situations. Next slide, please. So the data that I started was obtained from a public data set from Kaggle, and it overviews 70 different driving trips in the electric vehicle, the BMW i3. This data set was very expansive, and it recorded 28 different features, which may or may not have affected the state of charge in the car. In my paper, I have a table that overviews all these features, and it is quite a big table. So right now I'm only displaying a small portion of that table on your screen. And looking at the first measurement, the duration, you can see that the data was recorded every 10th of a second. This means that the data would be needed to take in at different intervals of time for us to feed it into the algorithms. These change intervals are called the delta. And where we begin taking the intervals is called a stagger. On your screen, you see a red and blue figure, which explains what the stagger is. Both rectangles are obtaining different data points every 2 units, which means their delta is 2. But the blue rectangles start obtaining data points starting off at row 2 instead of row 1, which means that the blue rectangles have a stagger of 1. And this way, you could have the same delta with a different stagger and have different results because it's essentially generating different data sets, which means the algorithm has more to learn from instead of just one data set, about 70 trips. So after going through a bunch of delta and stagger combinations, we generated 10 unique data sets ranging from delta 100 staggered 10, which is quite a large file, to delta 2400 staggered 20, which is on the larger side. Next slide, please. So now that I had these different data sets, I used the Pixie Navigator where I ran the data sets on algorithms, random forest regression, linear regression, and k-nearest neighbors. And these are three very well-known and inexpensive machine learning algorithms. And the main key here is that these algorithms can be deployed by almost anyone with an internet connection, and they aren't relatively complex either. So if these in-depth and robust algorithms could accurately predict state of charge, I believe that it could help increase confidence in the expensive and elusive algorithms that EV manufacturers deploy, thus increasing the public confidence in electric vehicles. In addition, this process can be shown to the public while electric vehicle manufacturer companies aren't going to be showing their processes to the public for privacy reasons. So these three algorithms are also different in how they go about the process of prediction. As you can see, random forest regressor uses a format which has yes or no classification questions, and linear regression uses known data to plot a line of best fit, and k-nearest neighbors will find similar data points to base its prediction off of. These are very simple explanations, and if you're interested, I encourage you to do some further research, but for the purpose of my presentation, these are the main differences between these algorithms. Next slide, please. So keep in mind that each algorithm from my last slide was only fed 80% of a data set to learn from, and the rest of the 20% of the data was hidden from the algorithm, and then we tested it using that 20%. So with the results from that 20%, I used the root mean square error, or RMSE, to measure the algorithm's predictions, which was comparing the actual data points in the context to the range of RMSE values to what the algorithm predicted. So through rigorous experimentation, I was also able to identify the delta and stagger combination in algorithm which produced the least amount of error in predicting the state of charge. And although I initially thought that smaller deltas, which would measure the data in smaller intervals, would help the algorithm to be more exact in predictions, they may have actually confused the algorithm. I say this because the most accurate results from my experimentation was actually from a delta of 2400 and stagger of 20. That was our largest delta. Data was extracted every 4 minutes. An explanation for this, like I said, may be that smaller intervals of change led the algorithm to track minuscule fluctuations, while larger deltas only recorded meaningful changes, leading to less error. As for algorithms, random forest regressor was the leading algorithm in terms of accuracy. Combined with a delta of 2400 and a stagger of 20, it produced the lowest RMSE, which was 4000. Next slide, please. So these experiments proved that AI can, in fact, very accurately predict the state of charge. As we saw, the mean error in the best experiment was only 4000, which is a very, very small number, and most likely wouldn't ever cause any negative outcomes for drivers. And it was also discovered that random forest regressor was the right algorithm to deploy on this sort of data. Although the other algorithms did not perform inaccurately, they just weren't as good as random forest. And also something to keep in mind here is that this data set was only applied to the BMW i3, so we can't be 100% sure that these results would apply to every electric vehicle, but because the nature of the data, it took features of the electric vehicle, and these features are universal features, it wouldn't be far-fetched to hypothesize that our results could be applied to other electric vehicles. Next slide, please. So, like I said, this was a research paper, and my final research paper takes a much more experimentation and has a deep dive into the results and sub-experimental results, including experiments by different seasons and feature importance charts. And so the preprint of my research paper can be found on Mobility RXIV, which is a website made by SAE. And the final paper will be published soon, hopefully, in the SAE Journal of Technical Papers. Next slide, please. So now that we have seen how critical artificial intelligence can be to the vehicle industry, it makes sense to continue research. And different paths of research that I believe may be important could include environmental impacts, experiments based on the state of the battery itself, like how old or new it is, and also look towards different types of electric vehicles or different brands and compare. This sort of research, like the research I have done, definitely has the ability to add to the plethora of evidence pointing to the great importance of AI for electric vehicles. Next slide, please. And that's it. Thank you for your time.
Oh, I'm so sorry, I was muted. Thank you very much, Shreya. It was a really good presentation. There are a couple of questions. The first one is, do you think this algorithm is generic to apply to other cars and not just the BMW? You spoke to that a bit in your presentation, but do you want to highlight what you said?
Right, sure. So as long as you have data set that is specific to a car, you can put it into any algorithm, because these algorithms are just taking the data in and predicting. It doesn't have to be certain types of data.
And then why do you think the smaller deltas, do they focus on smaller changes, or how should the audience think about the smaller deltas?
So it basically, smaller delta means we took the data points at smaller intervals of time. So smaller delta maybe took data points every 10 seconds, whether larger deltas took it every, or like every minute or every 10 seconds. Yeah, and larger deltas took it like at 4 minutes, which was the most successful. So when you're taking something every 10 seconds, you will start, the algorithm may get confused by small changes and make inaccurate predictions based on changes that don't really matter.
Makes sense. Thank you very much. Wonderful presentation. Thank you.
Thank you.